As we close Chapter 9, we're looking at 9.7 here is more of a discussion on probability. It includes some pretty basic ideas. It goes all the way up to some pretty advanced counting ideas and probability ideas. So this would be enough for several, even a whole chapter in a statistics course, but we're going to kind of rush through this here, and hopefully this will make some sense. The basics certainly will. The first idea is something called a probability model, and it's this very simple idea. All you're doing in a probability model is you're listing all the things that can occur and then defining out the probabilities of each of those events. So if you're rolling a dice, all the things that can happen, I would usually write this down, but we're going right to left here, but all the things, you could get a 1, 2, 3, 4, 5, or 6. Those are all the things that could happen. And then if there's 6 sides, the chance of getting a 1 is 1 out of 6. A 2 is 1 out of 6. So this is a probability model. All the things that can occur and the probability of those things happening. Okay, so if we were to do this for a coin, well, our outcomes would of course be you could get a heads or you could get a tails. Now our probabilities, and we'll talk about this more, I'm sure it's intuitive, that there's 2 things that could happen in each case, but there's one way you could get a head or one way you could get a tail. So this is my probability model. All the things that can happen and all their probabilities. Now, this looks terrible here, but this is what's really happening. If you want to set up the probability of something, what you need to do is the outcomes. Oh, I'm sorry. I'm doing this wrong. It should be successes over outcomes or possibilities. So what we're saying is how many possible things could happen. That's going to be the denominator. Sorry, I am butchering this. How many different things could happen is going to be the denominator. Then how many are we happy with? What are the successful outcomes that we're interested in? Those are the numerator. So if I have a 6-sided dice, the total possible things that could happen, there are 6 things that could happen. That's the denominator, the number of possibilities. Now, a success for me means getting an odd number. Well, how many ways can that happen? Well, I'm happy with a 1, I'm happy with a 3, and I'm happy with a 5. So there are 3 ways that I'm happy. Those are my successes. So 3 over 6 is my probability, which of course could reduce to 1/2. All right, so let's play this game again. So all the possibilities, there are 6 possibilities. Now, I want to get a number greater than 2. So I'm happy with 3, 4, 5, or 6. So there are 4 ways that would make me happy. That goes on top, 4 over 6, or 2/3. All right, now, it is possible that we're going to see a couple formulas here that look really complicated and it's like something that needs to be memorized. It's actually quite simple. What we're going to do here is we're going to add up the probability of 2 things happening. So this means I'm happy. Let me do my story here. Well, hold on. Jazz is a little bit dated here. Let's do rap or country. And yes, I cannot spell. Okay. So if I were to have a classroom of people, I got 30 students in my class, and I said, hey, who here likes rap music? And I have people raise their hand, and I get something like, okay, I had 17 out of the 30 people liked rap music. Well, if I said, okay, who likes country music? And I had 15 out of 30 people raise their hand. If I was interested in or, what this means is I'm happy with anyone who likes rap or country. Either one of those things would make me happy. So rap or country should mean that I add them up. I don't care if you raised your hand for rap or if you raised your hand for country. That's what I was interested in. I'm happy with either one, so I just add those. However, it's possible. I never said that you couldn't like rap or country music. There might have been a few people in the room who liked both. So suppose 3 out of 30 people liked both. Well, I counted them twice. So if you look at this as a Venn diagram, suppose this was rap and this was country. Well, there are some people in this area. There are some people who are in both groups. They raised their hand for saying, yeah, I like rap. They also raised their hand to say, yeah, I like country music. So there was an overlap there. They're in both groups. So we counted them twice. Do you see, if I counted the wrap circle and then I counted the country circle, this group in the middle got hit twice. I counted them already when I did the country. That's the second time that I saw them. So if you count something twice, just subtract it once. So I'm happy with wrap or country, but because there were people that were in both groups, I need to subtract that away. And that's what all this craziness is saying. This means or, and this means and. So I'm happy with E or F. Now I add those up because I'm happy with either, but I'm subtracting away any that are in both groups. Okay, so I am looking for, wait, what are we doing here? So I am happy, I'm looking for the probability of a heart or a 7. Now I'm happy with either one of those. So I'm going to add them up. So there are, is it 13? Yeah, it is. Okay, so if I'm in a standard deck of cards, there's 13 hearts out of 52 cards. So that's the way I'm happy with the hearts. But I'm also happy with 7s. Well, in a standard deck of cards, there's 4 7s out of 52. Now here's the problem. I have actually counted a card twice. There is a card that is both a heart and a 7. There's one of those. I accidentally counted him twice. He was counted for the hearts. He was counted for the 7s. I need to take him away because he was counted 2 times. There's a 7 of hearts. He was counted twice. So I subtract away the one time that I've counted to, so that was in both categories. So if we add this up, we've got 17 minus 1, we've got 16 over 52 is the probability of a heart or a 7. You could reduce that down to 4 over 13. Okay, so let's try another one. We want a red, probability of a red or an ace. Okay, well, a red, half of the deck, a 52 card deck, half of them are red. So you could have done 1/2, but I'm just going to keep it as the total number of cards. So 26 out of 52. Now, we're also happy with an ace. Well, in a deck of cards, there are 4 aces out of 52. But we've counted a couple twice. We counted the ace of hearts and the ace of diamonds 2 times. So if we've counted something too many times, we're going to take them away. There were red aces, so we've already counted them. They got counted in this group. They got counted in this one, so we need to remove them. So I've got 28 over 52, and we could reduce that down. All right, now mutually exclusive events means that they never overlap. So perhaps I said, instead of asking the class if they like jazz or country, or whatever I said, I don't even remember, rap or country, if I said, were you born in the United States or were you born in Canada? Well, you were only born in one place. It is impossible for you to have been born in both at the same time. So nobody was born in both the United States and Canada, so there's nobody in the and category. Nobody could raise their hand for both of those. And so all you do, if there's no overlap, which means mutually exclusive, the events can never happen at the same time. You just don't have to worry about that minus part. You can just drop that part out of the formula because there is nobody who's in both categories. So it would be impossible. So this is the same formula. It's still or. We just don't ever have anyone in both groups because they're called mutually exclusive. They couldn't happen at the same time. Okay, so if we're doing a heart or a spade, well, there are 13 hearts out of 52, and there are 13 spades out of 52, but there's no card in the deck that is both a heart and a spade at the same time. That's impossible. So we don't have to worry about subtracting. We get 26 out of 52, we get 1/2. Okay, now a really powerful tool, very simple one, is a complement rule. In a probability space, or probability distribution, I can't remember what we said, probability model is I guess what we're saying here. It was all the things that can happen and all their probabilities. Well, if these are all the things that can happen, if I wanted to find the probability of not getting a red card, that means I could take the probability of getting a red card, which would be 13 out of 52. The probability of not getting a red card is everything else. And the total probability has to be 100% or 1. So I could just say the probability of not getting a red is called the complement. It is everything else. If this is the probability of getting a red card, not a red card must be everything else. It must be all the other possibilities. So I could do a red card subtracted from everything would get me not a red card. So what we can do is we can take the opposite of what we want, subtract it from 1, and that allows us to find it. It's called the complement. So maybe this will make some more sense here as we look at some applications. So we want to find the probability of rolling, the sum of the numbers. Okay, yeah. So this is a little bit complicated. We're going to roll 2 dice, and we want the sum on the dice is equal to or less than 3. Now, if we list out all the possibilities, here's the first dice and the second. There's only these 3 choices that have a total of 3 or less. You could get a 1 and a 1, a 1 and a 2, or maybe you got a 2 and a 1. Those are the only choices. So the probability that is less than or equal to 3 is 3 choices out of the 36. Now, where did I come up with the 36? Well, there's 6 possibilities for the first dice, 6 possibilities for the second. You can multiply the choices together to get 36. Okay, so 3 out of 36. Now, how about the probability the sum is greater than 3? Well, I'm looking for the opposite. Isn't greater than 3 the opposite of less than or equal to 3? They're opposites of each other. So all I have to do is use the power of a complement. Doing the greater than 3 would be hard. I mean, I could get there, but it would be easier to just say 1 minus 3 over 36. So this is the opposite of what I want. But because of the power of knowing that it all has to be 100 or 1, I can just take the one that I don't want, take its opposite away from 1, and that must be the same thing as being greater than 3. These 2 things are opposites of each other. So I can use the complement to find the opposite. And so I'd have 33 out of 36. So I'd be making this like into 36 over 36. That's where I got the 33. Okay, let's see. Okay, so here's what I want to find. I want to find the probability that a sum of 2 dice is less than 10. Now that's a lot of options. Let's go back here. So the sum is less than 10. There'd be a lot of choices. But if I did, let's do the opposite because it's easier. Let's find, did it say less than 10? So the opposite of that would be 10 or more. Wouldn't that be these? Oh no, even more. It'd be this one. Sorry, I keep messing this up. These are the choices that would be 10 or more. So we want to know less than 10, but we could do 10 or more. There are 1, 2, 3, 4, 5, 6 that are 10 or more. So 10 or more is 6 out of 36. If I want to find the opposite of that, I'm going to do 1 minus 6 over 36. So that'd be like 36 over 36 minus 6 over 36. It's going to be 30 over 36, and you can reduce that. Okay, now this last one is a doozy. We got 2 left. One of them, the one they left for us isn't that bad, but this one is quite something. So this is as hard as it gets. See if you can follow me here. Sorry, excuse me. Here's a glass of tea. Okay. We have, let's see, 5 toys are taken from a bin. There are 3 bunnies, 5 dogs, and 6 bears. So here's the first thing I want you to see. There are 14 things in this basket. So there's 14, and we're going to be taking 5 toys at a time. So remember, probability is success over the outcomes, or possibilities, whatever you want to say. So what are we happy with, and how many ways are there that it can be done? Well, if I'm taking 5 toys from a bin, here are the total number of outcomes. Can you follow me here? 14 toys are in the bin. I just added this up, 3, 5, and 6. There are 14 toys in there. I'm selecting 5 at a time. So this is the possible number of outcomes. 14 taken 5 at a time. Now it's a combination because I don't care if I select the bunny rabbit first or third. It's the same bunny rabbit, so it doesn't matter. So the order doesn't matter. So this is a combination. Now let's start working number 1 here. What's the probability that only bears are chosen? So I'm only going to be happy if we select a bear. Okay, well, a bear from this, there were 6 bears out of the 5 toys. So here's my chances. There are 6 bears. I'm going to get all 5 of them that I've selected are bears. So what are my chances of out of 6 bears, I get all 5 bears? Well, there's 6 out of 5 ways this could happen, and it's a combination. Now, I want to put that over the total possibilities. So this is how many ways you could select bears. It's a combination. I don't care if I select this bear first or last or third, whatever, he's the same bear. The total possible outcomes is the combination, 14 toys taken 5 at a time. This crunches down to be the chances of getting a bear. Now, so we can crunch that number and I'll show it to you here in a minute. I'm just going to leave that as the concept here. Now, find the probability that 2 bears and 3 dogs are selected. So first of all, the bottom of this is going to be the same thing. It's 14 taken 5. That's the total number of ways you could pull a toy out of this bin. But what we're going to do on the top is, okay, well, how about bears? Combination of taking 6 and getting 2 bears would be this. Okay? That's the ways I could get a bear. Now, how many ways could I get a dog? Combination, there are 5 dogs and I get 3 dogs. So this first one, how many ways could I get the bear? The second one, how many ways could I get the dog? If this is the possible ways for the bear and this is the ways for the dog, you can just multiply those together. There's 2, or the combination of 6 taken 2 and the combination of 5 taken 3. Multiply those together, and those are the successes that I'm happy with. You would divide them over the total number of possibilities. Now, let me show, we're going to walk through this one with them. So they've crunched the numbers here for us, but it's just what I was saying before. Exactly what I said. Now, let's go to the last one. What they wanted, that at least 2 dogs are chosen. That's a difficult question. At least is going to be really difficult. And whenever we see at least, we should think about the complement. So instead of at least 2 dogs are chosen, I'm going to be interested in the probability of 0 or 1 dog being chosen. At least is difficult, but 0 or 1, I could do that. So let's see how we did it. So what we're going to do here, first of all, let's find the possibility that no dogs are chosen. That would mean that I'm selecting from everything else. So no dogs would mean I'm getting either bunnies or bears. And there's 9 of them. So, and I'm picking 5 toys. This would be I'm picking out of the 9 non-dogs, and I'm taking 5. There are no dogs here, so this would be a success. No dogs out of the total, which we've already seen. Now, how about we find you get 1 dog out of the total? Well, there's 5 dogs, toys, and you get 1. That would be the combination of 5 taken 1 at a time. Now, how about this one? The rest of the remaining 4 toys must come from the others. They must come either from, what are they? I don't remember what the other toys are, but the non-dogs here. So we're going to take 4 from the non-dogs. So we've got 1 dog out of the 5 and 4 from the other toys. You can, if this is one choice and this is the other, you can multiply them together, and it's still over the total number of toys. Okay, so this was no dogs. This was 1 dog and the rest of the other toys. Now, we are happy with either no dogs or 1 dog, so we can add those up. We're just adding the 2 possibilities, no dogs or 1 dog. I'm happy with that, either one of those, so I can add them, and I get this. Now, we didn't really want to know the possibility of 0 or 1. What we wanted to find was at least 2 dogs. and at least 2 dogs is the complement. So I know this is really difficult, but we're going to take the 1 dog or the 0 dogs and we're going to take it away to find the complement, which is at least, which is what we were looking for. So I'm taking that answer away from 1 because I wanted the other side. I wanted at least. Now that's super difficult. I know that's hard, but they're going to be a little easier on us here. Let's find this final question. We are going to take 3 gumballs from a container here. So we've got 4 purple, 8 yellow, and 2 green. Well, let's find the probability that 3 gumballs that are selected are all purple. Well, first of all, let's find the total possibility. So if we're taking gumballs out of here, there's 8, 9, 10, there's 14 gumballs, and we're selecting 3 at a time. This is going to be the total outcomes. It's going to be the denominator. So I've got C of 14 taken 3 at a time. Okay, now how about the top? How many ways am I happy? Well, I'm happy if all of them that are selected are purple. So I want a combination, because the order doesn't matter, 4 purple gumballs, and I'm going to select 3 of them. Okay, so if you crunch this down, that would be the answer to number 1. Now, how about no yellow gumballs are selected? Well, that's C. 14 take. So the bottom is still the same. There's 14 gumballs. We're taking 3 at a time. That's the same. Now we want no yellows. Okay, well, if no yellows, that would mean that there's 4. We're either getting purples or greens. So there's 6 purples and greens. We're taking all of them from the purples and greens. So 6 taken 3 at a time. And then lastly, find the probability of at least 1 yellow. Well, hey, at least 1 yellow is the opposite of no yellows. So all we have to do is take our answer from B and find the complement. There's my complement. Does that make sense? This was no yellows. If I want at least 1 yellow, that's the complement, and I have that worked here. Now I didn't do all the numbers, but here they are down in the corner. I'm not going to crunch these, but so you're finding the combinations of each of these, crunch them down, and here's the answers that you should get. All right, now that's pretty difficult. I mean, to put all that in one section is quite a lot, especially these last 2 questions. But start by making sure you understand those basic fundamentals, and then once you feel like you've got the handle on it, you can move to these more advanced questions at the end.